cover a little bit about streaming overview, who are some of the people in the marketplace, what is IBM doing there, a little bit on the languages that we use for IBM Streams, a little bit about the Python language, and then hopefully a demo. So first, what is streaming analytics? I was doing some things with database, and my boss called me up one day and said, Roger, there's this thing coming out of IBM Research called System S, S standing for streaming, that had been doing work with the US government, Department of Defense, for the last 6 years, saying how do we analyze all different variety of data that's coming so fast. If we write at the disk, it's not fast enough to analyze all the data that we have coming in. And the data could be video data, it could be image data, it could be sound data, it could be screen capture data, text data, transaction, all different kinds of data. And IBM Research said we have no idea how to analyze at the rates you're talking about and all that different variety and fusing different kinds of data together. If I recognized in facial recognition, which is, only moderately accurate, somebody that we think is a person of interest, how can I fuse that with geospatial information and go alert the closest law enforcement officer? So the research was a lot of very raw early stuff to figure it out. There was a lot of investigation into could we just do SQL in-memory databases, could we just do some kind of Java, and they finally said we should invent a new language because this really is a new paradigm to do streaming. So streaming, the idea is it can filter, aggregate, enrich, and analyze high throughput, exceedingly high volumes, up to potentially millions of messages or events per second, whatever you might call them. Different multiple data sources, any format, structured, unstructured, image, audio, etc. Put them in context and figure out what should we do right away. And there's now a large number of people that have entered that market. Some of our view of having a language that's unique for this is that each new trend in the technology era has said, let's try and come up with a language that is suitable for that paradigm. So Fortran for scientific back 60 years ago now, COBOL for business-oriented languages, C for system and higher level programming, C++ getting into object, SQL specific for database programming. It's now, what, 50 years old now? How old is databases in SQL language? 40, 45, it's old. Java for web programming, Python is a general purpose language for Python. And one of the things that's unique about the problem space we're trying to get into, which is very similar to Hadoop, is how do I scale a program across multiple machines? How do I write an application program and not have to worry, does it run on one machine, 3 machines, 100 machines, and scale up as needed? And that's really what these streaming paradigms have been. How do I take data that's coming from some sensor, that's coming from some data source, RSS feed or other, while it's still in a network connection, analyze it in memory, and then land it across multiple machines. So you see the visualization there. The idea is a record or an event is coming into the system. Those silver balls, we'll get into more of this coming up, are operators that we call in streams. They're a library that does some function. Read from a webcam, do facial detection, read from a PCAP file or a live PCAP feed from a network that's capturing all of the packets and allowing you to stitch the packets together to come up with, here's 5 seconds of audio, and then say, let's convert the audio into text, and then let's do text analysis. The idea is you string together those series of operators for how you want to do your application, split them to run in parallel, and then run that application across multiple machines, those gray boxes potentially being multiple machines in a cluster, that allows you to scale up and be able to get to millions of events per second or very complex kinds of analytics that's doing live text. The Hadoop paradigm, and more recently Spark, that allows you to do it programmatically in a Scala or a Python or a Java programming language, is another way to scale out across machines and not have to, like in the older days, figure out, oh, this is how much will fit on one machine. Let me now pass the data to a new machine and manually figure all that up with MPI message processing interfaces and interconnect and things like that. Let me just go the overall flow of the application and then figure that out. Makes sense? How many of you are working with any kind of streaming data right now? So 6 or 8 or 10, and what systems are you using to do that on?
Azure Event Hubs.
Event hubs?
Yep.
What kind of event hubs? So
Azure
event.
Yeah.
Okay, great. And you were doing some custom things, Martin?
Yeah, just on the desktop.
Just on a desktop kinds of a thing. Others? Other systems you're
Amazon.
using? What?
Amazon.
Amazon, so AWS Kinesis? Or just the
Not
Amazon
certain.
clusters and
Yeah.
stream it in there and do things? And there was 1 or 2 others that were, John? Not both. So that's the idea of streaming analytics. There's become a whole lot of people in the market. IBM shipped its first version of Streams in spring of 2009. Forrester did a wave in March of this year and said here are 15 different vendors doing this. Most of those vendors are really what used to be characterized as complex event processing. And for a while there was a difference in the marketplace perception of complex event processing as a single machine and its structured data. Same idea, event comes in, I go through some logic to decide what to do with it. But typically it was never unstructured data. Streaming has always been on a cluster of machines. So several of those that you see up there on the left who's doing this, Software AG is their offering called Apama. They're also in the center circle with IBM on the right. Lord did another study where he did not only streaming things, but to me some slightly different paradigms of bringing it into some kind of an in-memory database like KX or HP Vertica or other in-memory database, do SQL queries against it, then generate joins between the SQL queries, almost like joining multiple queries. Here's one for the historic data. Here's a SQL query for the last minute of data. Let's join those and see what the results are to, in near real time, come up with something. So a lot of different ways of doing those kinds of things. Other vendors that are up there on the left are SAP, which purchased some of the early CEP vendors. Alary and Correlate were purchased and came together underneath SAP. TIBCO has purchased one of the early vendors. Several other early vendors that are out there doing those things. Streambase is one of those, etc. So CEP, and they've now grown over the years. They now run on clustered runtimes as well. We typically don't have a strong support for unstructured data as the streaming things might. Other things that are out there, Storm, most people are familiar with, which Twitter has replaced internally and open source with something called Heron. Apache Flink is another one that's out there coming out of Europe. Apache Apex is another open source project. So there's a whole lot of different vendors that have entered into this space because they all see this really as where the Hadoop market was about 6 or 8 years ago. Very new early market to do stream processing and say there's live data, let me analyze it live as it's flowing before deciding whether I should put something on the disk. Make sense? Familiar with what you guys understand and are seeing? Forrester, and you can get this if you're interested in the report. IBM can give you a link or I can contact and send it to you. They went through, here's the criteria that we think are important to go look at. What is the architecture of your system? Can you run on multiple systems or not? What kind of management tools do you have? Is it command line only, as some of the newer open source things are? Do you have a nice full GUI to do these things? What are your tools to develop? Again, is it just some type of editor that you're editing in the code, such as with Storm and typing in your Java code to call up various APIs? Is there some full kind of UI that you can see on this? Yeah. Thank you. Oh, you do have a thing there. Thank you.
That's better, thank you.
I didn't find that button there when I looked earlier today to say, how do we kill the light? You should tell us when we're not doing the right thing. Please, we need help. How do you handle the streams? What are different operators automatically handle the streams? How do you split a stream so that you can run in parallel and go allocate it across multiple cores or multiple nodes in the system? What facilities do you have for that? What facilities do you have to join that in for the stream handling? Stream operators. What are the functions that you can do that come with whatever this offering is from the various vendors? Do you have just the simple operators to do splits and joins? And I'm amazed at how many things don't have aggregates in there. I was a little bit surprised to learn Spark Streaming, which is a capability off of Spark. Just 3 months ago was saying, yes, we're going to add some aggregations. How do I do a windowed aggregation to just very simply say, data's coming in, just give me a sum of all of the data that's over the last 5,000 records or over the last 30 seconds, and do things like that. So those were some of those operators are more advanced things like geospatial capabilities, audio capabilities. Some of you heard earlier, we showed Stuart Hanna, who's hiding in the back corner, in a video that we did where we've done some interesting things with the North Sea Oil Company that said cod are an endangered species. We need to try and better learn when the cod are busy spawning, because when they're spawning, you're not supposed to be making a lot of noise and disturbing the environment. There's much stronger environmental laws, and that includes the undersea environment. And so we put some underwater microphones in. We found some university professors that have done lots of research, and it turns out that the frequency, the sound wave frequency that cod grunt is different than other kinds of fish when they're busy making babies. So you can listen, you can graph that, you can see that, you can detect the fact that yes, the cod are busy spawning. Please alert the oil rig operator, shut down everything so we leave those coddies alone to make new baby coddies, so in a few years we can have more cod on our plates at dinner time. So those are different kinds of operators that might come. How do you build the apps, visual text? Do you ship any applications with it? Acquisition and pricing. Reason IBM only got a 3 on that is we don't have a free open source version of Streams that we sell. And so they said, oh, sorry, you have to have a free version or an open source version to do that. We've chosen to say we're not going to open source this. Still has update. We continually relook at that type of thing, but still it's open. And then do we have the ability to execute on our strategy? What is our strategy there? This was a comparison I did. We did a benchmark a few months ago with Walmart. Walmart was very interested in understanding who has the best performing system out there, because I have lots of stores that I want to do many different kinds of real-time analytics on it. First application is to monitor heating, ventilation, and air conditioning units centrally for all 6,700 stores and be able to understand of the hundreds of refrigerators and freezers are in each store, have any of them been open too long so that you should alert the store manager, please go do something. It appears someone wedged something in the doorway, it's not closing properly. We don't want the doors to be open so long that there's spoilage and things like that. Not to mention the energy costs and other things. They also are looking towards the point where Amazon, being only an online type of vendor, can change their prices thousands and thousands of times per month. Walmart, being mostly an in-store vendor, doesn't change their prices very often. So how can they do more with real-time inventory, more with real-time pricing to better compete against Amazon that started born off the web instead of born in stores and things like that, like Walmart does. But we put together with Walmart this sort of comparison. What are several of the open source things? Esper is one of the original CDP engines. Storm, originally built by Twitter. It's an Apache project now. Several people have picked it up and used that in their Hadoop distributions. Cloudera and Hortonworks both ship Storm, replaced by Heron, which Twitter made available as open source about 3 or 4 months ago. They internally have totally replaced Storm with Heron. Flink came out of Germany, Spark Streaming, data flow out of Google, higher level language solutions. And you see, many common things across all of them. They're all programmatic. I can build in a higher level language, not just like MapReduce kinds of things. I may or may not have some interface to manage the tools and things. And the biggest difference from an IBM Streams is the visual types of tools that we have, and more importantly, the many different libraries that we have to make it faster to build some of these kinds of applications. And also, is it open source or not, as I mentioned earlier. So IBM Streams Offering, as I said, it came out of IBM Research. First release was in 2009. I'll go through a little bit of that really fast and see what some of the language looks like so you see that language. And then we'll get into what is Python, and then we will try and show a demo. I have 2 or 3 who was trying to make another one work that some of my developers came to me, and we'll see how that goes. But Streams comes with an Eclipse-based IDE so that you can build these applications in a visual drag and drop type environment. We also support Java, so that from Java you can just code all in Java, and much like Storm or Flink, call, or Spark Streaming also, just call certain libraries that are then compiled in to go and run on the runtime. And we've also developed Python capability for that as well. So you can develop directly all in Python, call all the different streams libraries that we have, never having to learn the streams processing language, and then go execute it on the streams runtime for high performance. The scale-out runtime is Linux machines, standard x86 commodity servers or IBM Power hardware to run on, and one machine if the volume is small. My largest customer is the Department of Defense that's doing national security types of things with cybersecurity and video image. They have a cluster that's 100 machines of 32 cores each to do that level of processing. So scale out runtime, dynamically add nodes, and dynamically add jobs to that, and then all these toolkits that I've mentioned also. Something coming up, this is public so I can state these kinds of things. We do have a new release that will ship in third quarter, which is coming to a close fairly soon, so I can't officially give you the date because we have not officially announced it yet. But there's only about, what, 31, 32 days left in the quarter, so it should be coming very soon. Many of IBM's customers are in the Internet of Things types of applications. Automotive, Peugeot is a reference customer. Honda has been monitoring their Formula One race car engine, which is a McLaren engine. Sensors spitting off all the time, about 2,000 different variables to try and understand what's going on in the engine. Cummins engine has been in production for a year now. They build huge diesel engines in trucks. And they remotely get the data and then centrally get what are all the engine faults, what's the history on this, so that they can then send a message back to the truck operator. Based upon these faults and the way your engine's been operating, we recommend you get to the closest Cummins authorized repair station. Here's where it is. You should get there within 4 hours, otherwise your engine's going to have serious problems. They all came to us and said, this is really great, but those cell phone charges to bring all the data in from around the world, across the country, is expensive. Can we do more analytics at the edge, on the engine itself, or in a car itself? We did another pilot where we put streams into a car, in a laptop, in the trunk, and accessed all the engine data. So we built an open source version called Apache Agent. It is an Apache project. It's streaming at the edge, runs on Java, has some of our libraries within it that do those windowed aggregations that I mentioned earlier and several other things. We'll do more things in this next release to have federated applications, run some analytics on the edge. When you detect a certain thing of interest, send it up to the central site. Now with more data, correlations potentially across many things that are the same kind of a thing, the same automobile type, for example, get more insight to that particular automobile or vehicle and send specific information down to it. Rules, IBM has long had an offering called Operational Decision Manager, which is one of the leader in the business rules management arena. We'll add a capability so that on streams in the Eclipse UI, you can write English language level rules. If the temperature's gone over 100 degrees and it stayed there for 5 minutes, then I would like you to be able to send a message out to the plant operator. So we'll compile those into streams and run them natively on the streaming engine. And then Python development, which we'll show today. I can show that because we developed it all in open source. You could download and play with it today, even though this next release isn't there. The other thing, a couple key things, the speech-to-text toolkit, we took from IBM's Watson cloud service, their speech-to-text capability. And we've had this running at a telco for the last 6 months. They've got about 200 operators. We're tapping into their voice over IP network, building up the whole voice stream for both speakers in their call center, converting speech to text, doing text analytics to get to the root cause, and then be able to display on the operator screen, here's what we think is the root cause, here's the suggested next best action. By August, early August, late July, we've done about 25 million minutes of speech to text for this North American telco with no failures of the engine. So we said, let's put it in the product and ship it so other people can start to take advantage of that capability. So that will be there relatively soon. Those are some of the key things that are in coming up real soon. All right, so overview of streams. Streaming, like we had in that earlier video, is a series of operators. It's a flow graph. If you're familiar with BPEL, somebody once told me, if you've done Unix piping together of jobs and applications, that's all this is. I have a record or a file, it's coming through, I have one operator that's a library that does something. In this example, I might read from meter data, cleanse it by saying, the meter data should always be in this range. If it's out of that range, just throw it away because it's a bad record. So cleanse some of the data, filter it. One of my customers is Centerpoint Energy. If they ever write log messages to a disk drive, they have to save it for 7 years. Because the PUC says, you store any data, you have to save it, we might want to look at that. So they said, well, a very simple application is before writing the log message to disk, let me just send it to this streaming analytics engine and say, is it a message that says, I'm fine, I'm fine, I'm fine, I'm fine, which most of the day, most computer networks are fine. Take all those messages and throw them away. If there's ever a state change, I'm not fine, or you can't receive the message, then flag an alert, maybe write that to disk because it's worth saving and important. So a number of different things, and you can write in Streams processing language, or you can do any custom Java or C code that you have, and now Python code. There's a way to wrap that and use that in the IDE and then compile it and deploy it out to the runtime. The languages, we call them, has a bunch of operators, source, input operators. How do I read from a Kafka queue, from a TCP IP socket, a web socket, a JMS message queue from the major vendors, from a webcam, a lot of different input sources or input from databases or files that you have addressed. And then these series of operators, what do I want to do with this function that we talked about earlier, aggregations, machine learning kinds of things. Let me read the data in, build up a model, and then start to make predictions with a number of different machine learning algorithms. And then sync operators, what do I want to do at the end of this streaming job? I might throw it away, I might say I want to save this in a disk because it's important for future people to see. Like if I'm monitoring electricity data, I might want to send an alert if it ever goes over some spike, but I'd also like to aggregate 15 minutes of data because that's what I use for my billing records. So let me persist that to a database or a Hadoop cluster or a number of NoSQL kinds of databases like Redis or other things like that. That's then in Streams processing language. In another slide, I'll show you quickly what that looks like. I then compile that, optimized compiler, which is part of how we get all of our efficiencies. We compile the code to exactly what you need, so there's not if-defs and other things in the code when it's compiled. When you do an aggregate operator, if it's for 50 records, we have exactly the size of memory for those 50 records and know how to do the aggregation, to do a sum or a standard deviation or a min or a max and those kinds of things. And then it's deployed out to the clustered runtime. And that's just a quick list of things that I've been talking about for a little while, and many different adapters. We will get these slides posted, right, David, onto the Meetup site so you can have these, and there's nothing confidential in any of them, but the arrows are bi-directional, so I can read and write from the different communication sources that are there, and read and write from all of the different persistent database kinds of things, or NoSQL stores, and then a bunch of different functions. There's over 150 operators that we ship with Streams. On a GitHub open source site, we decided several years ago that adapters really aren't any proprietary value add. So let's develop a lot of those things in the open now on a GitHub site. We did this because a customer a few years ago said, I love your directory watch operator. Watch a directory, and anytime a new file lands in there, read it and process all the files in it. But we'd like to, after we do the read, we'd like to erase it from that directory and put it into another directory called completed. And I said, that's a great idea. We can do that in about next release in 9 months. And they said, not worth waiting for you. I can write my own operator in Java to do exactly what I want to do. Use your XML descriptors, and now the IDE and compiler knows how to use my operator to do that. And we said, well, why don't we make a bunch of these things open source? So if you want to enhance my operators, you can at least start with some of the open source and hopefully contribute back into that so that other people take advantage. And then when we do releases, we just cobble up the open source, new things, test it, document it, and ship it out. Any questions on any of that stuff that's there? These are some of just the toolkits that we have. Mining in microseconds has several things. We can import predictive model markup languages. We can run R models that you have. We can run SPSS models. There are predictive machine learning, as I said. There's about 19 different machine learning algorithms that are native in streams to learn as you go. Cahonen clustering and k-means clustering and ARIMA regression kinds of techniques, and Holt-Winters, which is a seasonal predictive algorithm. There's a number of things to just learn on the fly and then make predictions. Some advanced mathematical models that we've had from IBM, often as a services asset for key engagements. Acoustic are also in that, although, as I said, with this next release, we will ship acoustic and speech-to-text capabilities to be able to take, unfortunately, first release English language only. I'm glad I'm not doing this right now in Spain or France. It wouldn't go over quite as well. But speech-to-text to do that capability. Image and video, there's an open source toolkit for image and video that Intel wrote called OpenCV. We don't ship that with Streams because of the license on it means I would have to open source all of Streams. But we do have on the GitHub site the OpenCV toolkit wrappered so that you could just download that into your Streams IDE and be able to drag and drop those operators to do facial detection and facial recognition and contour outlines and a whole lot of things on streaming data, and then write it out to a display or a file so that you can actually see now what's changing in the video as things are going on. Geospatial, distance calculations, map mapping calculations to do a number of things. Natural language processing is text analytics, so ability to understand parts of speech, be able to create dictionaries of different kinds. Here's a dictionary on sentiment or other kinds of things to do social media or other kinds of analytics. So lots of different things come with the product. You get it, it all comes. And I didn't put a slide on this. My marketing person will probably be mad, but there is a quick start edition, which is free to use for development and test. You just can't run an application in production. And it's full function, it has all of these stuff. If you go to ibm.com/streams, there'll be a link, try it, and you'll get to a place where you can download the IDE. It comes in either a VMware edition that's pretty large or native installation onto Linux, so if you want to try and run it on a cluster, you can do those kinds of things. So all that comes with it. The one that probably won't come with it, unfortunately, is that new speech to text, because the models are so large, it doubles the size of the image. So we haven't quite figured out on the free version how will we make that available to people. So we're still looking at some of that stuff from packaging. IDE, we'll look at this a little more closely in a second, but just the language you see there, and I'll have a bigger slide so you can read it and walk through that a little bit. And then visual composition tools to just drag and drop. Here's all of the operators that you can drag and drop, and hopefully I'll show the IDE a little bit. A few words that we use. An operator is that function library of code which does something. Stream is an infinite sequence of structured tuples. Tuples is a word that we use in Streams as the formal word to explain this is a message or an event or a record. The technical guys say it's a tuple, sometimes pronounced tuple, because it contains unstructured data. Now, it's one of the first things I learned in Python. Python also uses the word tuple. It's like a list, except it's an unmutable list. So there's a different meaning in Streams versus Python for that little word tuple. Stream type, we specify what is the schema. Streams is a strongly typed system, again, different than Python, which is not a strongly typed system. You have to specify what is the schema of each record that's coming through. And I'll show you the data types in a second as an example. And then a window is just some grouping of those tuples which came through. So hopefully you can read a little bit of this. Let me go first to the example because I find that's easier. Streams is a declarative language. What this little block of code is doing is declaring a new stream called sail. That new stream called sail has, as we said, strongly typed, so it is a raw string with an attribute called item. I create this stream by using an operator called join, which joins together two other streams, which are named and defined somewhere else in the program, called bid and ask. And this is a stock trading kind of an example. And I want to join them together by looking at windows of data. For the bid stream that's coming in, I want to use a sliding window and have time, which is a 30-second window. Sliding window just means when the window is full, you do the function. When a new record comes in, you slide out the oldest record and have the 30 most recent records, or 30 seconds worth of most recent record. The ask window is count, so 50 records exactly, and then take the operation and then slide out when you get a new one. We also support natively tumbling windows, which says as soon as you do the operation, throw away all of the data. Sliding windows are good for things like rolling averages, if I want to do temperatures or stock or other things like that. And we also use it in the speech to text to just make it a little more accurate. If I have 5 seconds of speech, I'd like to get a rolling window of 5 seconds, because if I stop speech at, I'm never quite sure did I get a whole word or a partial word. So sliding windows are good for speech kinds of things as well. Tumbling is great when you're doing averages or sums or other things like that. Just give me 30 seconds of data, take the sum of all the records in there, and then just save one record, because that's all I care about. Or give me an average of that, because I'm just trying to monitor temperature data throughout the day, and I don't need to save 100 records every second. A 5-minute average is good enough for saving and persisting. And then parameters, you have ability to put some logic. I want to make sure that the item being asked for and the item being bid on to buy are the same item. They're both IBM stock. And I want to make sure that the price of bid is greater than or equal to the ask price. And then if those parameters happen, then output a record into this new stream called sale and get the data for item from the stream that came in called bid. So all of the operators in the language looks like that. That's the format of what they look like. I have people that come to me and say, yes, if I'm a Java programmer or a C programmer, I can understand your syntax. It's another language and it's different, but it's another language. And all of this is visual. You can drag and drop, double click on the operator and it pops up and you just fill in little examples for what's the parameter you want to use for sliding window, time, or count based on those kind of things. So it's a language that we designed specifically for stream processing kinds of things. As I mentioned, it's a strongly typed system, so we support a bunch of very specific data types to be able to, yes, question?
In your example, how do you know the two streams are in sync?
How do you know the two streams are in sync? You mean the two that you're joining together?
Yes.
So as the windows fill up, the logic that's built to go do that just determines we've hit a 30-second window, that's we're going to take this action, or we've taken the count window and it's full and we take the action. There is in the parameters that you specify in the join operator, at what point do you want to take the action? It could be just a partial window that you have on some of the others if it hasn't filled up yet. If you say, I want to take the action based upon this stream coming in, doing it every 30 seconds. But there's a lot of flexibility in the library that we have in making the decision, when do you want to take the action that you're doing for this particular function, and what do you want to have as your eviction policy? Those can be different. Okay, thank you, good question. So we said it's a strongly typed system. That's part of how we get a lot of the performance in streams, is if you know that you only need an 8-bit integer, then we're only going to, when we create those aggregate operators and save in memory, enough for that, enough for 8-bit integers to be summed. One of the techniques that we use. We also, when we compile these things together, compile many operators into a single process, and then we can do context switching. You can say in the language, this particular stream is going to be mutable or unmutable, meaning the schema will not change. I might change some of the data in there, but I'm not going to enrich and add an extra attribute into the stream that's going out of this operator. As long as I know it's the same linked in memory, I'll just pass a memory pointer to the next bit of logic to do the next operation on it, as opposed to making a memory copy. So we've been beat up by the government and many customers for years to say, drive this as fast as you can, because I have more data than you can possibly handle. So we've done many benchmarks. The one that we did with, just a little bit more on the logic and application is that flow graph. It can be cyclic, so you can have in the logic of your program some downstream operator that detects a condition of interest, send a record back up further into it as control logic to change the behavior of your application. So it is a cyclic application, and you can do a lot of complicated kinds of things in that. I think most of those others we've said. The stream connection, we connect into, you see little, in those orange boxes that are there, a source operator sending the data to two sinks. When we compile, those records are actually copied. A copy of the record will go to both operators, so you can do things in parallel. You also have split operators that say split on this particular operator, like a stock tick, and be able to run 5,000 averages of stock ticks in parallel across multiple parallel streams. But those little tiny boxes there we call ports, and sometimes you can have multiple ports coming into an operator, one for data and one for that control logic. We do that, for example, with R and SPSS logic, that you have an ability that if you're running some model, you can have a downstream operator that says this model has drifted. The average confidence level always used to be 92%, and now it's drifting down to 91, 90, 89%. It's drifted so far. Let me send some control logic out to go rebuild the model. With SPSS, we can do that. With R, we can have some manual processes that update the R model, because now there's more historic data to build the model. And when that model is built, the control port comes in and says, I've got this new model up to date. What the operator does is put back pressure on the incoming tuples for a few milliseconds so that we can, in real time, update the model and always have a continually updated model. So that's what the stream connections are and those control ports that we have. We fuse the operators into a processing element that I mentioned. That's what's deployed out to the runtime. And then a job is just the application that's compiled and running. Usually people build up larger applications from multiple jobs. Any of the jobs that you have can have one of the streams exported, so another job could dynamically import into that, kind of like a pub sub model. So that one job might be just doing ingest and cleansing of data, and then exporting the data stream to another job which does the logic, makes it easier to maintain the logic of your code, drop in a new logic model that might now get duplicate copies of the record just to test and make sure, yes, this new model that we're trying out, this new logic for some type of analytics is better. And therefore, let's take away the old job, which isn't quite as good. So lots of sophisticated kind of things. This takes you just through running. Here's that flow graph that we mentioned. A job has source operators that do some logic, and then sync operators. Each of those is then compiled to what we call a streams instance. A streams instance might be a single host. When you compile the job, it creates these processing elements that we mentioned, and an instance might also be multiple hosts. You don't have to recompile the job or do anything to deploy out to a different instance. You can just deploy it and say, go start running the job now on an instance that has 4 nodes. I'm doing stock trading and it's a heavy stock trading day. I want 4 nodes instead of my standard 3 nodes. And the deployment manager will automatically spit out and break up the code across multiple nodes to go do that. This is an example of a benchmark that we did with Walmart. It was called the Linear Road Benchmark. It was a benchmark Michael Stonebreaker and a few others created about 15 years ago in the early days of complex event processing. And the idea is I have fictitious roads. And every mile there's an entry and an exit. And what I want to do is feed data that is cars coming into the roadway and positional statements, where are they on the roadway. And then your stream processing engine has to do multiple things. It has to be able to do a little bit of cleansing on the data. It has to be able to report and detect that there's been an accident, so traffic is slowed down, and be able to give warnings out to other people. It has to give travel time estimates on that linear road, and it has to be able to go back 10 weeks when someone does a query, what was my toll charge on on a day 6 weeks ago, so I understand that. And then the idea is for a fixed amount of hardware. Walmart gave us a total of 6 Azure nodes, which we ran the application on 4, and ran management services on a 5th, and had a 6th just for standby. Used Redis across all of those to maintain the state. The idea is, how do I start going from 1 road to 2 roads to 3 roads to 6 roads, or as many roads as you can handle, and finish the workload in 3 hours on that fixed amount of hardware, and then I can compare vendor A to B to C to D and see who we think is the best. One other thing they did there is, in that going from 1 road to 2 roads to 3 roads, we used a capability that we have that with a single line of code called an annotator, you can say, take this portion of the code, the application, and please parallelize it. You can say parallelize it at compile time, 5 times, 10 times, 200 times, or make that a runtime parameter. When we submit the job, parallelize this 200 times, and then deploy it across the runtime and go run the application. So when we did this, these were the results that we had. We actually ended up with an L rating of 50 roads on a single 16-core Azure node that was doing about 100,000 average events per second coming in, peak as much as 200,000 events coming in. And then when we scaled out the 4 application nodes, we scaled almost linearly to 200 expressways, and then we couldn't handle the job in 3 hours. And Walmart was great at feeding the data. They wrote some great data drivers to do that, and a validation routine that validated all the data was correct. And you see some of the volume numbers there. Sorry, the weight at the top is kind of hard to read, but it's number of expressways, and then it's number of cars, up to 55 million cars on 200 roads. How many messages or tuples came in, either as position reports or those queries for accidents or toll charges. 3.8 billion. How much memory did it take, and what was the CPU? Walmart, and I didn't include this slide, but Walmart put together something that we did at a conference where they said another vendor came in to try Storm with this benchmark, and their L rating was 20 on those 6 nodes that they were allowed to have. So Walmart said, if Streams can handle 10 times the number of events, or excuse me, 20 times the number of events on the same hardware, you don't have to buy a license from IBM for that. I'm saving 20x on the hardware. And on Azure, running 100 nodes was going to be 110,000 a month. Running 5 nodes was going to be 5,000 a month. All right. So the idea of Streams and Python together, we for years with Streams have said, I don't want to learn a new SPL kind of language that you've invented, IBM. I already am a programmer, I know Java, I know Python, can I use those? And especially for data scientists, which is a very important market. We're doing a lot of things with Hadoop and Spark. And our SPSS family also is a bunch of stuff in that area. Let's do Python. So here's an example of this. Let me import. That's one of the capabilities of Python. Very easy to import libraries from other places, even out from websites that are somewhere else. Just import this library function that we have. So let me import my module, and let me get it from Streams X topology, get the context, and then you're declaring a function called topology, and in the function it's just in quotes hello world, which is a text string, and assigning that to topo, which is a variable that you just created there. And then let me end up printing that out to a sync, which goes back to some of the keywords and functions that were imported from the Streams topology. Going back to that Streams lingo of a sync is, I want to send it out of the Streams program. Once that topology is defined in that language, it can go away to the Streams compiler. This is admittedly, and you'll see this, really slow. Because what we do is we take that Python code, compile it into Streams processing language code, which then under the covers gets compiled into C language code, which anybody can look at if they really want to, and then machine code, and then deployed to the Streams runtime. So you will see that all those steps going through means this is kind of an ugly and long process to get through. But that's where we are in the state of the art thing. But it gives, for me, that ability now to go to developers and say, these 86,000 programs, the ability to quickly iterate on things in a notebook, test them out, try the underlying logic, and then later add into a Streams data flow before you go to a final test. means you're speeding development by having new functional kinds of capabilities. When we support Python, we have really two different types of things that we can go do. The first is designed for the SPL developer. We've added a capability that you can decorate in your streams processing language program and just have a decorator that says at spl.pipe. The next little block of code is native Python. The streams compiler will then just say, oh, okay, this next little block of code is Python. I will recognize that it's Python and allow you to use that within a streams application, which my developer just told me they added this like 2 weeks ago. They hadn't let me know they were thinking about this and doing this, and they said it works and it works and it does this. What I think will be interesting is, remember we said streams is strongly typed, and Python is not strongly typed. So when I say a variable A is less than B, I don't know if it's an integer, a floating point, or other things. The Python compiler tries to be really smart, and based upon the data that you fed in to initialize those variables, will say, yes, I know this is an integer, so I'll assign it into that class of data types. Because again, Python is object-oriented, everything in Python is an object. So you can understand what is the class of that and understand it's a class integer versus a class of floating point for numbers. And hopefully, what they've done in this, and I presume they have, I haven't challenged too much to test to make sure, but they say they've tested so it works, is to be able to query when we compile what is the class of that data type, so we know within streams what is the data type that we should assign into the stream of things. So that's just a simple function. We're going to filter if A is less than B, and then if A is less than B, I want to return a value that says A plus B. We can put that directly in there. And I put, so when you see this, all of this Python code for streams was developed in open on GitHub. You can go to github.com/IBM Streams and be able to download all of this stuff, see the documentation, try it out, and then we'll formally ship when they're released, as I said, this quarter. Nope. I skipped a screen. No, I'm sorry. I went through this one. This is for the Python developer. Let me write it all in Python, and the second one is for the SPL developer. Let me just decorate a Python function and add it into my streams code. I'm not going to go through all this, but I want to document it so you have it in the charts if you want to try it. You can try all these things today by downloading the Stream Quick Start Edition. As I said, no charge. It is full function. You can do all development and all testing with it, just no production. Is the license agreement that's on that. And then go out to the GitHub site where we have the topology, clone it on down, download it to machine, run AMP, do all the different things, update the path names that you need to for Linux, etc. And then we downloaded the Anaconda notebook to be able to go say, let's use that as a Jupyter. It has a Jupyter notebook from Anaconda. So I'm getting my words mixed up there. But it's a Jupyter notebook from the vendor Anaconda that includes with it the Python capability. So we'll show that in one or two different ways in just a moment or so. And then several other things to be able to get it started and go running. And one developer that helped work on this gave me several demos. One was just a net demo which he had, which did three things. Let me generate in Python some engine temperatures and failure expectations. Let me use a quick little Python function which will do a best line fit into that with some regression algorithms. And then let me feed that to it runs in real time in streams to be able to use a predictive model to predict is the engine going to fail. And do some things with that. The other developer that she told me last Friday, Roger, I think I will have a demo for you that's going to be getting the EKG data and using that PQRS waveforming and spiking things. I won't know if it's going to be ready to give to you until Monday. Well, Monday I was driving 14 hours from Perry, North Carolina to get up here, today moving in. So we spent like 30 or 45 minutes looking at this. And we'll try it. I'm not sure it's really going to work though, but it'll be interesting. So this is when you download Streams Quick Start, what you end up getting. And now I'm also challenged because I have to look on the screen there and on the screen here. I love the dual screen thing. So it comes with a full runtime engine, instructions on how to get it started up. And what I've got are several just browsers running to go say, first off, when you get started, there is something, the Streams console, which has things up and running. It's all web-based, be able to manage the system and visually see how many instances do I have running, on what machines. And you see at the dashboard across the top what's continually running. Domain are all of the machines that you have. You typically will have multiple instances, one for development, one for test, one for pre-production, and then one for production. You can manage all of these from the console. And then how many jobs do I have running? How many PEs are there, the processing elements, which are compiled into from the operators? And then how many operators are running, and how many streams are there? The streams are those things that connect one operator to another. So you can quickly see the status of all of those, drill down, and be able to run and execute all of those kinds of things. So this is one example of the Jupyter notebook that was actually up and running. What this first net demo application did, as I said, is in the Jupyter notebook. He's got several blocks of code. And this first one, when you click on the block of code, you're allowed to be able to hit in the Jupyter notebook, all right, I want you to go ahead and run this code. It will run this code. The first application, they said, is just a generator of data in Python to be able to go create some random numbers that are just numbers to be able to compare engine failure or engine temperature versus a probability of failure. The second part of this little demo that Will wrote for me was to say, all right, let me go create a best fit model. Again, these are standard Python kinds of things, importing some existing code from different places. He imports the data set that we created from the prior job, and that's another nice thing that you can do with these notebooks, is easily pass data sets and other things from one part of your job to the next part. And then let me go run that cell. And now you see the line fitting kind of thing. We'll do a best fit line on that particular data set that I have. And then let me say, all right, how do I go create this model and actually use it on the Streams runtime that's also in this VMware image that I'm running on my laptop? And again, so if I click on that, this has several things that we showed earlier in the Hello World example. You know, I want to import the Streams topology. I want to import some things from the Jupyter utilities to be able to graph this and import some of the data sets that I've created. And then you see, again, Python logic to what is the test data that I'm going to have, what are the specific operators that I'm going to use from Streams, how do I go build that graph, how do I then submit this job to the Streams runtime. And that was from an earlier run, but let me go through some of this and show you again. If I run that, oh, I don't want to do that one, do I? No, it goes through, as I said, a relatively long compile process because it's going to take that Python code and compile it into Streams processing language code, and then take the SPL code and put it natively into C language, and then whatever the runtime happens to be that you're running on machine language, and then deploy it out to the machine. If I were to go to the console, it should be able to. Yeah, there it's actually building out the data that's going out on there. Let me see if I can also show you that other one that I had that was in a window. This is actually my development team that's up in Toronto set up for me. Roger, we'll set up a Streams machine for you in there, and I can browse into it. You can tap into there. So they set up for me a separate machine up there where they said, let me give you some other applications that we've written, and this one was a Streams job that would dynamically reach out to physio.net. Physio.net is a public health database that has anonymized data for all sorts of physiological data that they've collected, such as EKG waveform readings and things like that. So one Streams job was running And that's one of the jobs that is running right now. It has the 4 PEs and 4 operators and 4 streams to go out to PhysioNet and be able to collect that data and bring it back so that it can be used on that machine in the Jupyter notebook that's running on that machine, which I'll just browse into to be able to go show. The Python application is up there that just imports several pieces of data to run a package called BioSPPY. That is that application which can look at EKG data and say, here is the peak of each R wave, which is the very top of that waveform that a heartbeat waveform does. And it goes through what are all the things that we're doing. Well, gee, we're invoking the SPL make toolkit, which means I want to take this and in streams processing language, what we do is we will make that and compile the application. So it's calling all of these different things. What are the different toolkits that I need to get to go into streams? And it does a lot of things. This is not like Python, simple and non-wordy when you're looking at the console kind of things. And then the next stage of this application, you do see the code there, and we can make these examples available to people. And with that, we may just have a final summary slide. The Python is a language that a lot of people are coming up with and saying, we would love this, it's cool. These notebooks, we will type little code snippets, test it out very nicely, iteratively, make sure it works. Capabilities that you have to share the files and collaborate on things are all very cool things. Now there's a really cool package that will calculate where's the peak of a waveform, so you know what that is, and then you can very quickly, once you know the peak, start to be able to go see what are the differences in the peaks, put it in something called a point vary plot, which one of the doctors that we work with at Emory Hospital said that's a very interesting display. Because what you really want in heartbeats is variability. All hearts, as they're beating, have natural variability. Your 72, 73 beats per minute, 76, you change a little bit. Somebody walks in, you change a little bit. The waveforms change a little bit. And that's normal to have that variation. When people are very, very sick in the ICU, they start to conserve all energy, even down to you don't see that heartbeat normal variation. So with some of these data, and that's what they're looking for, and that's running live at Emory Hospital and a few other hospitals that we work with, is that heartbeat not varying? If it's not varying the way it normally is, then it's very likely the patient will die within 24 hours, and you need to start taking very aggressive action. You're already doing some because they're in the intensive care. You have been very attentive in listening. I appreciate you sticking around with me and my failure to do demo. I apologize for that. You might come off and play with it later if you want to stay, but I don't want to hold you for longer than that. Are there any other overall questions that I can answer? You were good and attentive and didn't ask too many. Yes, sir.
Is there a dividing line between streams and Internet of Things? Or is it just a question of speed?
Is there a dividing line between streams and the Internet of Things? No, we have streams used in many Internet of Things applications. As I said, we have many customers. Internet of Things to me are the things that are generating data. And the question is, after that thing has generated some data, what do you want to do with it? But the market, I think, is starting to use a broader term. Internet of Things are applications to manage the things, to analyze the data, and take actions. And so I think there is becoming an overlap in streaming analytics. On the Internet of Things would be a subset, because you might do streaming analytics on text data, which we wouldn't normally think of as things.
All right, fair enough. Thanks.
Other questions? Yes, sir.
Can you compare it to IBM Watson?
Compare Streams to IBM Watson. Streams came out of IBM Research like Watson did. It came out 3 or 4 years earlier than Watson did. Streams was targeted at this problem, how do I analyze data in motion in real time? Watson was targeted at how do I understand natural language processing in text and be able to answer questions or create questions from answers for Jeopardy and then extend that to lots of different paradigms. They both have analytic capabilities. I would say that the Watson APIs that you have on Bluemix are more targeted at data at rest It's stored, it's saved somewhere, and now I want to do some of these kinds of analytics. You can send it a file and do other things with APIs. And there's also a mixture. As I mentioned, this one telephone company, the speech-to-text that we're going to be shipping with Streams is the Watson speech-to-text library. So we take that, we wrap it, and it becomes a Streams operator by defining it. Now it's drag and drop, do speech-to-text with this audio data that's coming in. Watson predominantly is on cloud. Streams, I do have versions on the cloud. You can try that out. Most of my customers are on-prem, either because of privacy type things, they're still concerned about the cloud, or just the data is generated and I want to analyze it right there. I don't want to come across a cloud. I want to fast filter it. Thank you for your time and attention this evening.